Hey, how does everyone feel? I feel half alive personally, but so I'm going to sit down here. Is that okay? Yeah, okay. Thank you. Can I put my feet up? Yes? You're trying to hurt me, aren't you? Because if I put my feet up, I'm clearly going to fall. Good. That's just not going to work so well. All right, so today, I would love to finish this chapter. I don't know if we can quite do it. I know it's also been very disjointed. I went back and just sort of scrolled through the video that we had from Friday's class, and also looked at the list of things that were covered in Friday's class, and just looked at the notes and tried to figure out where everything stood. And I know we've been sort of jumping around in chapter 11 and 12, so I know that you're probably confused. So before we move forward with the last little bit, just before this slide, I want to sort of summarize what's out there to give you a feel for what we've covered and what we know and kind of get all the equations in one place. Keep in mind, whatever we're about to put here is by no means comprehensive. There's other stuff in the chapter. This is sort of the primary thing so you can sort of see the basic outline of what's going on. So let's see. We could say, first of all, the effects of magnetic field on moving charges. So in this case, we've got a magnetic field that's already there. Something has created it. Well, it's moving charges that are other moving charges. And now we have moving charges passing through this magnetic field. And we have to look at how that affects these charges which are moving through the field. So we could make a very short list here. And we could say, first of all, we have a magnetic force on a single moving charge. A point charge is moving through a magnetic field, and it's going to feel a force only if it's moving. You might remember, or you might not remember, that the equation for this particular situation is QV cross B. It's the charge Q, and then the cross product of its velocity vector with the magnetic field vector. Okay, so clearly just from that, if the velocity goes to zero, there's no force. All right. We could rewrite this in terms of just magnitude, and that's going to be QVB sine theta, where theta is the angle between the velocity vector and the magnetic field vector. So as expected, there is a right-hand rule that's associated with this to give us the direction of the force. So I'm going to write the right-hand rule just under this in different colors. So what we're going to say is that we'll start with fingers in this direction. That just looks weird now. You know, it's like official physics stuff and then fingers. It's odd. All right? And then for B, we're going to say that you curl the fingers toward this direction. And then once you do all that, the result happens over here. And that's the direction that your thumb will end up pointing. And this is specifically for a positive charge. Okay? So I know some of you maybe do this a little bit differently, but maybe I'll take all four fingers of my right hand, point it in the direction of the velocity. From there, like the magnetic field is somewhere else. Maybe it's over this direction somewhere. Maybe it's over that direction somewhere. Maybe it's up somewhere. I just want to orient my hand so that when my fingers curl, they're moving over toward the direction where the magnetic field is. Okay? They don't necessarily have to be like perpendicular or anything like that. We just want there to be that relationship where I start with the velocity and turn the fingers toward the direction of the magnetic field. When we do that, thumb is in the direction of the force on that charge, if it's positive. If it's negative, just flip the direction when you're done. Okay? That's sort of our first right-hand rule. Number two, we can step this up and say, well, what if I have a bunch of moving charges instead of looking at just one? And it really turns out we get the same effect, and as I step through it, maybe you'll see that. We can have the magnetic force on a current carrying wire. Magnetic force on a current carrying wire. So now we're sort of stepping it up in a macroscopic way. So I have a bunch of moving charges that are passing through something that's physical, and I could actually experience the force on this wire as current moves through it. So the equation for this sets up almost exactly the same way. Every part of it has an analog. So instead of one charge, we now have a bunch of current, okay? Instead of a velocity, we have a direction that current's moving, and for that we use L to represent the direction the current's flowing. And then we're going to have a cross product with the magnetic field vector. So, of course, this is going to have this relationship as well. It's going to be ILB sine theta. Exact same right-hand rule. Okay? So let's just draw a little line down to this. Whee. Same right-hand rule. Okay? So instead of dealing with the direction one charge is moving, you're just thinking about where all the charges are moving. They're moving through the wire in a particular direction. Good so far? Yeah? Okay. There is a subset of this one. If I have two wires that are near each other, well, then I have two things that are making magnetic field and also two things that are feeling a force. So we could say that if we have two wires near each other, they experience a force. So let's call this the force between two current carrying wires. And how to write this? We're not going to deal with any cross products or anything here. We're just going to have a magnitude for this particular force. And it works out to be mu naught over 2 pi d, where d is the distance between the two wires, times the two currents, times the length of the wires, assuming they're the same length. Okay, mu naught over 2 pi d, I1, I2, L. Same length. Okay? Those are the effects of an existing magnetic field on moving charges. Question over there. Mu naught over 2 pi d. No, but part of that term is coming out of the magnetic field. We took a couple of equations there and sort of mashed them together that came from the creation of the magnetic field and the force. You'd have to look back in the book or in my video to see that derivation. I think I did it in the video. But the magnetic field, yes, is kind of hiding in there, at least in part. Question back there? This L vector here, okay, this is a vector in the direction of the current. And it has the magnitude of the wire itself. Okay? Anybody else? That's sort of the first step of this whole thing. Yeah. The subscript for force is B for magnetic field. This one, that doesn't really look like anything. There we go. That's a little better. Okay? Those are the effects of the magnetic field on moving charges, both one moving charge and a bunch of them. Okay? After we do that, we could now look at perhaps the creation of magnetic field from various circumstances. The key is that it always comes from moving charges. But of course, I can have moving charges in a variety of different configurations, all the way from one charge, all the way up to a bunch of charges, moving in all sorts of different patterns. Okay? So let's see. How do I want to say this? Let's list number one here. We've got a long straight wire. For a long straight wire, the magnetic field that's created is given by mu naught I, where I is the current, over 2 pi r, where r is the distance from that wire. And we're going to step back from this today and learn something new that's a much more general case. Because clearly, wires aren't always just long, straight wires. This is just the most simple situation that we can deal with. If we have a long, straight wire, there is a right-hand rule associated with this. The right-hand rule to get the direction of the magnetic field. There's no good way to do this other than just list things out. You can point your thumb in the direction of the current. And we'll say that finger curl, how's that? Gives you the direction of the magnetic field around the wire. If you put your thumb in the direction of the current, your fingers hopefully naturally curl in the direction of the magnetic field around that wire. If your hand works differently than that, my apologies. I don't know what to say. I'm sorry, I guess. Okay? First one, long straight wire, all right? Number two, what if we take that wire and wrap it into a loop? So let's call this a current loop. I'm not going to worry about the equation here. It's not something that really comes up terribly often. That equation for a long straight wire is sort of all the time happening. You can look up the specific equation for a current loop. I gave that to you in the slides. Instead, I want to focus on the direction from the right-hand rule, because that's going to get used a whole lot more often. You could, if you wanted to, use the exact same right-hand rule. It'll still work, okay? But if you just need to know the direction in the center of the loop, there's a bit of a shortcut. So you can use this, or we'll say alternate. For center of loop only. And if you decide to go that route, then we're going to sort of flip things around. And we're going to say that finger curl in the direction of the current. So if I have a loop, it's going to be going around that loop clockwise or counterclockwise. Let your fingers denote that. They curl in the direction. Set things up so that your fingers are pointing around that clockwise or counterclockwise direction. Once we do that, your thumb will give the direction of the magnetic field in the center of the loop. Okay? Any additional questions so far? We're almost done with summary time. Feel like there was something else to add to that. Not quite. Okay? This is sort of where we stand. There's a lot of other little details, but it all builds on these things, all right? Creating the magnetic field, and then the effects on charges if you already have a magnetic field. What we're going to continue today is this bottom part. We haven't quite finished up the creation of the magnetic field. So I'm just going to go ahead and list, we'll say 3 and 4 down here, and then we're going to go back to the regular slides and learn all the details of that, all right? So first of all, maybe I don't have a particular situation like a long straight wire or a simple current loop that I've already solved for. Maybe we want, we'll say, a more general equation. Or we might put next to this, wire not straight. And what we're going to use for that is known as the Biot-Savart Law. And that's what we're going to do next after I give you number 4. And finally, we will say some special symmetric cases. And this is sort of a subset where we can find the creation of a magnetic field from a particular wire that's oriented a certain way if there's certain symmetries, and you'll see how that works. For this, we're going to use something known as Ampere's law. And once we do it, you might see it as a more simple version of Gauss's law. All right, it's the same idea, the same concept. It's just we use it for currents and magnetic fields instead of charges and electric fields. Okay? Any questions about anything that's up there before we go to the next slide and learn about the Biot-Savart law? No? Nothing? You're good? Okay. That's where things stand. So, Biot-Savart Law. There we go. Isn't that beautiful? Notice here we're given the slight case of a little bit of curve in a wire. It's still a long wire, but instead of being perfectly straight, it's turning a little bit, which means using the simplified case that we had before isn't going to work for all positions around the wire. Things are changing a little bit in the direction of the current as I move down the wire. So what we're going to do is talk specifically about finding the magnetic field being created by this current at one point around the wire. So as soon as things start not being straight and things are curving, all of a sudden the calculation of the magnetic field quickly can get really, really complicated. So this is only going to allow us to find it at one point. If I wanted to find it at multiple points, I'd have to do this over and over and over again, and computationally that's going to get a little bit difficult, all right? So what you might imagine is we're going to do something similar to what we did before, and we're just going to look at a little piece of the wire. You could think of this as maybe a small bit of current. And it's traveling in the direction of the wire. And from that little piece of current, there is some distance out to this point where we're trying to find the magnetic field. So we're going to do exactly like what we did with electric fields, and we're going to have to consider every little piece of current along this wire. So we've got a bunch of little DLs. All of which contain the current I, and all of which sit different distances from that point. Okay, and we're going to have to add up the contribution of the magnetic field from all of those different little points. It turns out in this class, we're not going to deal with very complicated situations. Okay, so I'm still going to have to even take a situation like this and maybe form it into something symmetrical so we can get there. So in other words, you're not going to have to say, hey, I want the magnetic field at this point, and here's the wire. That sounds terrible. This is what you would use to calculate that, but we're not going to do that in this class. Instead, save that for your future career. Have fun with that. I think it's going to be awful. Okay, so don't worry about anything like that. Let me just give you the Biot-Savart Law. Let's see. Let me make sure that I get it right. Where is it? My notes are all backwards now. So let's see. We can say that a little bit of magnetic field that's created by a little bit of current is equal to this. Mu naught I over 4 pi times a little bit of mess. All right? Be patient with the things that exist in this next term. I will explain all of it. DL, maybe we already understand. It's a little bit of the length of wire that's carrying the current I. We are going to have a cross product with that particular vector and a new vector that maybe will haunt you a little from last semester. It's R hat. Ooh. So we've had fingers and thumbs and hats in today's lecture. Weird. DL cross R hat divided by R squared. Okay? Let's describe what all of these things are. So DL, we already know. Let's do this. We'll draw a little arrow there to say that's a small bit of current along the direction of the wire. This R hat thing is a unit vector. Aha. Anybody? Last semester? Unit vectors, long time ago. I see a few people who are like, you look a little disgusted. That's fine. Don't worry about it, okay? We will say it's a unit vector. Remember that unit vectors have a magnitude equal to 1. They don't really change anything. They just sort of point in a particular direction. So it's a unit vector, we'll say, from DL, the little piece of wire that we're considering, to the point where we're trying to find the magnetic field, point P. It's a unit vector that's basically just saying, like, hey, I'm a little bit of current, and I'm making a magnetic field everywhere. I'm worried about the magnetic field that I'm making over there at that point. And it points from the current segment that you're looking at out to the point that you're concerned about. So you can see that over in the diagram. Okay, the R hat vector goes from DL and points out to the point that we're trying to find the magnetic field at. Okay, and there's clearly going to be some angle between those two. Let's see. We can, if we wanted to, if you needed to find R hat specifically, I should point out that it is equal to the R vector divided by the magnitude of the r vector. That's what allows it to have just a magnitude of 1. And then finally, this one is simply the distance from DL to point P. How's that for a fun equation? It feels like one of the more difficult equations we've had in the 2 classes so far. There's a lot that's going on there. Okay? So if we want to find the total magnetic field at point P, we're going to have to integrate dB over all the little pieces of wire that's there. And to help you understand how this works, we're going to do an example, and it is not going to be scary. You may think I'm lying, but it's not going to be. This is going to be a ridiculously simple example. How did the test scores work out? Well, there's a lot of silence. Are you mad at me? Well, I actually saw some nods there, I think. Let's try again. Are you mad at me? You can say yes. Yeah. A little bit. No. Maybe it's the people who aren't here that are more mad. They're just like, I don't go to class. Yeah, I know. You're watching this video now. How was the exam? Oh, that was mean. I take that back. That's just a joke. I totally take that back. You don't have to be in class. It's fine. I like you to watch the videos. So let's do an example of this. Sadly, we've got another exam coming up before too long, don't we? We've got next week, then we've got spring break, then we've got a week, and then there's an exam. It's kind of a short gap between exam 1 and exam 2. So we are going to look at a situation we had before. And I think we've already done something like this where we found the electric field and maybe even the electric potential from just a loop of wire that has either current in it, or I think before we just had charge that was distributed throughout that loop of wire. So imagine this thing that's over here is a circle, but we're looking at it from the edge, okay? So there is current that's sort of going around this thing, but you can't really see the three-dimensionality of it. Instead, just imagine that if you just look at the bottom, this is the point where current's going into the screen, and then it goes up and around the back side of that loop, and then it's coming out of the screen here, and then goes around the front side, okay? So hopefully you can sort of turn that around and see what the current's doing. It's creating a magnetic field everywhere. Really, really quickly, you should be able to think about what this magnetic field looks like using one of the right-hand rules, right? So I can curl my fingers in the direction of the current in this orientation, okay? That tells me the direction of the magnetic field right through the middle. So you might start to get the idea that if I were to draw the magnetic field through the center of this, it's going to kind of like be going this way, and more than likely like wrap around like this, around both sides, and it looks kind of something like that. Please don't draw that in your notes. It doesn't matter, all right? I just want to make sure that we're connecting this to things that we've done before. So the magnetic field looks something like that. We are only going to use the Biot-Savart law to find the magnetic field at this one sad point that's on an axis that's directly through the center of the loop, some distance x away, okay? So before we can do anything, we need to consider the direction of the magnetic field at that point from all the different points on the loop of current. What they've drawn in this diagram is just considering a little piece of the loop directly at the top that's pointing toward you, okay? Are we okay with that? Not too scared, okay? If I'm just considering a little segment that's straight, let's flip the right-hand rule around and use the other one so that I'm going to point my thumb in the direction of the current at that point. And just think about the magnetic field created by that little segment of the loop. Everybody okay back there? No, maybe. You're all right. I don't know. That was loud. Oh, wow, these metal water bottles again. This must be a thing like after, I don't know, I got old or something. Like water bottles switched from rubbery, plasticky things to metal. Did that happen? You've only known, yeah, I don't know. You don't care. Fine, let's keep talking. This is more fun than talking about water bottles. So, thumb in the direction of the current, right at the top, it's pointing at you. Since I colored that in, and let me put that little dot there again. So think about the magnetic field around that top part of the loop. It's going that direction, like this. Ooh, right? And then think about which direction it points on that axis down below. You can already see they've given you the answer, but does that make sense? No, it doesn't, right? Let's go over here and imagine a little bit of current here coming out at me. I would have a magnetic field that goes around. Oh, that is not a circle. Let's see if this will help me. Can I actually center it on the thing? Oh, that's not too bad. And now we can imagine, let's see, this is the magnetic field at that point, and here it's going around this way, and here it's going that way. And if I go right over to this side, it's pointing up that direction. Okay? So this is the distance r. And maybe that, you can see, agrees with just the magnetic field from that top little segment of wire. Does that feel a little better? Okay, if we were to extend this out, I don't know. The magnetic field at different points is kind of doing something like this. How's that? Yeah?
So dB is the tangent to that point?
dB is tangent to that point. So it's perpendicular to the vector that gives me the distance away. Okay? Anybody else? That's just the magnetic field being created by that top tiny little piece of wire. Okay? You can see they've drawn a perpendicular and a tangential component, okay, or a parallel component. If you now extrapolate that around the loop, you need to think about what those three vectors are going to do. Like maybe start by just flipping it all the way to the bottom and think about what the vectors are going to do. If I were considering this point, everything would be exactly in reverse, and I would have something that, well, looks like what? We would still have a component this way, and there'd be a component that way, and I'd have something that looks kind of like that. Okay? That is the magnetic field from this little segment at the bottom. Mm-hmm. Shouldn't it be horizontal? Let's step through it. So let's go to the bottom part where I have current that's going away from you, and now we get a magnetic field that goes around that little part like this, which means that we get something that kind of, it's like around like this direction. It's all pointing this way. So that at that point, we have a vector that's down that way, and we have those components. Okay? You might get from that if I were to work all the way around, what's essentially going to happen is that for each one of these, where's my pointer? There we go. We're always going to have a component that points to the right. That's going to add. And this vector that's perpendicular to the x-axis is just going to work its way around in a circle. So there's always going to be a y component that has another y component to cancel out with. So the perpendicular components are going to cancel, and the parallel components are always going to add. This is like what we did before, but I think it's a little harder to see. How was that? Look at that. It almost took my neck off, but at least it didn't hit the floor. Okay? So let's do exactly that and work through our example. Let me take this thing and move it out of the way a little bit. Where can I put it? Oh, there's no place. Let's put it up at the top. Can I make it smaller? Will it let me? Nope. Now you get the idea. So let's start with the Biot-Savart Law. Let's see. dB is equal to, I don't remember it because it confuses me. Mu naught I over 4 pi times the, let's not do the integral yet, times dl cross r hat over r squared. And then we'll step through every little piece of that and put it in the integral and do the work. So let's put underneath this, we already said that the parallel components will add, and the perpendicular components will cancel. So we're only going to worry about the perpendicular components. So let's see, how can I switch from dB to dB parallel? Which trig function are we going to use? It would be the cosine, right? So let's see. If I just want the perpendicular components, we could say that B total is equal to B parallel, and I think I'm switching perpendicular and parallel in my head and saying the wrong word. My apologies. Which is equal to dB cosine phi, and we're going to add all of that up. Notice we're using phi just because that's what they used over in the diagram, so the cosine of that angle is going to give me the component that's on the x-axis. Yes? You can think of it kind of like our x and y components before, but they don't stay in the x and y directions necessarily. So it's perpendicular and parallel to the x-axis. Perpendicular and parallel to the x-axis. So the parallel one is always going to be along the x-axis, but the perpendicular one like goes in a circle around the x-axis, so it's not always the y direction. So it's better to say perpendicular and parallel instead. It's always x. Yeah, in this problem, yeah. In this problem, the parallel component is on the x-axis. In this problem. We could be using different axes in another problem. Okay? So let's take that thing from above, plug it in, and see what all happens. All right? So let's see. What are we going to have now? Let's just put the cosine of phi out front. Why not? And then we'll have our mu naught I over 4 pi and dl. And let's go ahead and write this as dl magnitude r hat magnitude. I'm out of room times the sine of the angle between them over r squared. Did I leave anything out there? So the cross product is the magnitude of the dl vector and the r hat vector times the sine of the angle between them, and we have an r squared in the denominator. What is the angle between dl and r in this problem? What's that? It is 90. Why is it 90? Do you see it up here anywhere? So if we go back to our diagram, we could say that the r hat vector points in that direction, and dl is perpendicular to the screen. So even though I can't draw theta in this diagram because it's sitting perpendicular to the screen, it's going to be a 90-degree angle. Something perpendicular pointing at you, and anything in the plane of the screen is going to be 90 degrees. Yeah. Where did we get sine theta? Sine theta is coming out of this cross product. We're evaluating the cross product to get the sine theta. Okay? Let's see. Let me go back to my notes here. So this is 90 degrees, which means that whole thing is just going to give me 1. What's the magnitude of r hat? That's just 1. Okay? So you can see that this complicated thing very quickly starts to turn into something we can do something with. Okay? A lot of stuff is just going to be 1 or 0 hiding inside there. What all do we have that's constant? What can we take out of here? What's that? Mu naught. I like mu naught. Let's see, B total. So we'll take out the mu naught and the I and the 4 pi. What else? R squared is also constant. I would agree with that. Anything else? Let's leave it at that for right now. So we'll go ahead and put this, and then what do we have inside still? We've got the cosine of phi and dl. Is that all? Or am I getting lost in my own work? No, I think that's all so far. Problem is now I've got this in terms of 2 different variables. So I need to go all one or all the other. So we can look back at the diagram and look at phi, which is given up here, and we can write the cosine of phi as the radius of the loop divided by r, the hypotenuse, or that distance from the loop over to the point we're talking about. Yeah? Why is r hat 1? By definition, unit vectors have a magnitude of 1. all unit vectors. Yeah, it's basically just there so we can evaluate theta. I need to find the angle between these two things that are pointing. But the magnitude is always 1. Okay? So let's see, cosine of phi. Let's do that part. So now we've got mu naught I over 4 pi r squared. Cosine of phi we just said was r over r. Well, all of that is constant too. So let's go ahead and sort of wrap this up. So now I've got mu naught I r over 4 pi r cubed times the integral of dl. What is the integral of dl here? dl is a little bit of the loop. What if I add up all the little bits of the loop? I just get L, which is the circumference of the loop, right? So that's going to be 2 pi times big R. So let's go over here. Since we're out of room, we can say that the total magnetic field at that point is going to be mu naught I times, I left out an R, times 2 pi another R over 4 pi R cubed. And then a couple of things cancel and combine, and then we're done. So let's see, the pi's cancel. That 2 cancels with part of that 4. And now we have mu naught I big R squared over 2 little r cubed. And hopefully I didn't lose something in that very long process. Double checking, that actually looks good. So weirdly enough, this time the hard part is getting things started, I think. Trying to figure out that cross product and getting the integral started. Once you get there, I'm again going to try to avoid giving you integrals that are like ridiculously complex because that could get hard really fast. Your question. The bounds. I left it indefinite. Just the fact that we're trying to consider the magnetic field coming from all parts of the loop means that my integral is over the entirety of the loop itself. So if you wanted to, you could just say that this is maybe just 0 to L, and then you would just get L, and L is the same as 2 pi R. Okay. Yeah?
What's the point of having r hat if it's just 1?
The point of the r hat is the theta. So it points in a certain direction, and I need to know the direction between its pointing and the magnetic field pointing, or excuse me, what is the other part of it? And the dl. I need to know the angle between those two. That's the whole point of the r hat. Anybody else? Yes? To r hat? dl is pointing directly out of the screen, and r hat is in the plane of the screen. Those two things are perpendicular to each other. The screen itself and anything perpendicular to it has an angle of 90 degrees. Mm-hmm. But at the top of the wire, when we're talking about just that little part, it's just a little segment of wire that's perfectly perpendicular to the screen or tangent to the loop. Yeah. Mm-hmm. Anybody else? I know this is kind of a confusing topic. It's one of the harder things that we're going to do is dealing with the Biot-Savart Law. So are you ready to do the big loop-de-loop curve thing? I don't think any of us are. All right, I can't blame you. All right. So let's see. Well, we've got 11 minutes left, which might be just enough time to do what I want to do. So the next few slides are kind of out of order. So this one, let's jump from that one to the next one, okay? Ampere's Law. Let me describe Ampere's Law, and then I'm going to show you a quick example, or maybe two, since they're so extremely short. And then, believe it or not, some of those later slides we're not even going to worry about. So Ampere's Law looks like this, and it will look very familiar. We have a closed path integral of B dot dl this time is equal to mu naught times I enclosed. B.dl is equal to mu naught times I enclosed. So instead of having a surface area this time, we're not going to have a surface area. We're just going to have a closed path, a closed loop. So everything is sort of happening in one dimension instead of having to deal with this two-dimensional thing that's encapsulating a three-dimensional volume. So it's like everything is dimensionally down one, which is just, I think, easier to process in every way. The easiest way for me to explain how this works is for us to go back one slide, which should actually be the next slide, and show you how it works for a simple long straight wire. Okay? For a long straight wire, we can use Ampere's law to get the exact same equation we had before for the magnetic field that's being created by a long straight wire. So what we're going to do is, let's see, we will draw a little path around this, and I hate that they kind of already did it. So let's do this again. Let's draw a wire here. It's got a current that's going this direction. And we're going to look at a circular path that sort of goes around that wire and has a radius r. So if we had a Gaussian surface, I don't know that anybody uses this terminology, but maybe we should call this like an Amperian path, I guess, by analogy. I don't know. Let's put quotes around that because I don't know that that's an actual term. Just keep in mind, it's not something that's really there. It's just the place where we want to know the magnetic field. Every point on that path should have the same value for the magnetic field because it's the same distance away from the wire. So the same sort of principles are applying like before. So if we work our way through Ampere's law, and I like this because this is so ridiculously simple that we're almost done. Like you write the equation down and then all of a sudden it's just over. So let's see, if the magnetic field is everywhere constant on the path, we can pull it out on the path. And then we just have this integral of dl once again. And on this side, we have a constant mu naught. And how much current is enclosed by the path? How much lives inside that circle we drew? I. That's all the current that's inside that path. So we're just going to write that as I. That's kind of weird and kind of fun all at the same time. So now all of a sudden we have B, and the integral of dl is just the circumference once again. So that's going to be 2 pi r equals mu naught times I. So B is equal to mu naught I over 2 pi r, and we're done. Wasn't that fun? And that's the same equation we had before. Ta-da-da-da. How easy is that? But let's not leave it at that. Yes. It's just the place where we want to know the magnetic field. We want to know the magnetic field at some distance r away from the wire. So we created a little imaginary loop that has a radius r such that every point on there has the same magnetic field. Yep. Let's do one more real quick because they're just so simple and easy. All right, we're not going to do this one. Don't worry about that slide. We are going to do this slide. So this time, notice we have a wire that we're not treating as just sort of like a one-dimensional thing. We're going to say like a wire actually has thickness. And there's like charges that are flowing through there at all points. And maybe I don't want to just know what the magnetic field is outside the wire, but at different points on the inside of the wire. Okay? So if I were to try to find the magnetic field outside the wire, that's just the same as before. Nothing has changed. We get the exact same solution, the exact same path to that solution. It all works just like what we just did. The key is if I want to go inside, how does that change? Inside the wire, we might use a little Amperian path that looks something like that. Okay? At some distance r, that's less than the radius of the wire itself. So we'll say for r less than big R. So don't blink or this is going to be over. So B dot dl is equal to mu naught times I enclosed. Once again, the left-hand side is going to be B times 2 pi r for the circumference. The only complexity here comes from I enclosed, because now if I is passing through the entire volume of the wire, the I that lives like inside here is some fraction of the total amount of the current. Not all of the current is enclosed by that path. But to find out how much is there, it's just a fraction of it. I'm just going to write it as a fraction. It's essentially a percentage of the total. So what I could do is write this as something like, we'll say 1 cross-sectional area. The cross-sectional area, that's the path itself, divided by the total cross-sectional area. Okay, so this thing is just the fraction of the total current. And yes, I still need an I out there. And then we solve for B, and that's done. Okay? I like the I enclosed concept. It just kind of seems weird. It's like, well, there's a wire that has current passing through it. Did you hug the wire? If you did, then you use that current. Like whatever current that you've hugged is what you're going to use. So you can rearrange and solve that for B, and it does come out to be mu naught times I times little r over 2 pi big R squared. Just rearrange things and cancel some stuff, and you get where you want to be. Okay? Yeah. Question? Anyone back there? No? Yeah. I'm sorry. Which D where? DL? It represents, if we were to go around here, like a little bit of this path, working our way around that Amperian path or circle. All right, there is only one other thing I want to tell you in these slides, believe it or not. I actually didn't think we would finish because it's like some of this stuff may take longer to explain than I thought. So this slide I want to give you an equation on. We're not dealing with a toroid, and we're not dealing with this last thing. So I want to give you one little thing here because it comes up often. It turns out that a very common structure that's used is not just a loop of wire, but a bunch of loops of wire. So something known as a solenoid is just, we'll say, many loops with current. So you can see we just took the same wire and just wrapped it around over and over and over and over and over and over again. What this has the effect of doing is like take the magnetic field from one current loop and like multiply that effect over and over and over again. It's like I took one loop and I stacked another one right on top of that, and another one right on top of that, and another one right on top of that. And every one of those loops is creating its own magnetic field because the same current is passing through it. Okay? So what you get if you densely pack these loops, and typically they're not going to be so loosely wound like you see there, they'll actually be smashed up against each other, is that you get a very strong magnetic field passing down the center of the solenoid and a very weak magnetic field because of cancellation effects happening on the outside of the solenoid. In a way, this is kind of analogous to our parallel plate capacitor, where we had a strong electric field right in between the plates and kind of nothing happening on the outside. This is like the magnetic version of that. Very strong magnetic field in the middle and kind of nothing happening on the outside. Okay? I'm just going to give you the equation for this. It turns out this whole thing over here is using Ampere's law to find this equation, but we're not going to have to worry about how to do that. And also just look at that. It looks weird. So strange things are happening. I just want you to be aware of the solenoid and be able to use the equation and use it in the lab as needed. So let's see. This is the magnetic field, we'll say, in the middle. So down the center of the solenoid, it's going to be equal to mu naught times little n times I. This little n is known as the loop density. So it is simply the number of loops divided by the length of the solenoid. Okay? Believe it or not, that's the end of the chapter, right on time. But did we cross out those other slides? We did. 11 and 12 is done. Friday, we will jump back into 13 and probably finish it up. And yay. Aren't you excited? Yes, question. Go back to the last slide. I'm sorry. Yeah, there we go. Okay. I'll see you all on Friday. Have a good evening. Have a good tomorrow. Have a good 47 hours without me. Yeah, count it down.